the fourth lecture on partial differential equation. Today we shall apply or solve Laplace's equation in spherical polar coordinates having spherical symmetry, and we will discuss about the cases of spherical symmetry. In the last class we solved Laplace's equation in spherical polar coordinate and obtain the solution as r theta. The general solution we obtain as L is running from 0 to infinity for a given L. M ranges from minus L to plus L, and the radial solution was obtained as the theta equation is ALM PLM cos theta plus BLM QLM of cos theta e to the n phi part is e to the power I n phi. So this is the associated Legendre function of first kind, and this is QLM is the associated Legendre function of second kind. This is also called the associated Legendre polynomial. If the system under consideration includes cos theta is equal to plus minus 1, that is z-axis, then one must set BLM is equal to 0, as QLM has divergence on z-axis. Has divergence on z-axis. So we set, for that case we set BLM 0. This is the general solution. One more thing. If the region under consideration includes R is equal to 0 region, then one must set BL is equal to 0, because otherwise there will be a divergence. And now the special case, if the system has azimuthal symmetry, that is the solution is independent of phi, then M must be 0 and this sum is no more there, and the solution is and in that case this AL, this is Legendre polynomial, simple Legendre polynomial. This is for azimuthal symmetry. And there is another interesting case, the system having spherical symmetry, in which case the solution depends only on R. It doesn't have any theta dependence as well. In that case, the solution is obtained with L is equal to 0, and the solution is A plus B by R. This is the solution. This is the solution for system having spherical symmetry. Here we have obtained the most general solution, and then on freezing one degree, that is 5, by freezing the 5 degree freedom, we have obtained the solution for as having azimuthal symmetry, and then if one robs off the theta dependence also, then we get the solution, spherically symmetric solution. This solution can also be obtained by solving the Laplace's equation for spherically symmetric cases, in which case this for spherically symmetric case has only R dependence, so that we have R square sine theta. We need not to use del del. This is R square sine theta dr is equal to 0. This is the radial part, and that is to this sine theta part cancels out, and we have r square dr. Dr is a constant, a and or d of capital R is equal to a to the power minus 2 dr, or capital R of R is equal to minus a by r plus another constant b, which is of the form thus. So now we apply Laplace's equation for spherical symmetric cases in two different cases. Now, firstly, we consider a spherical capacitor. A spherical capacitor comprises of two concentric spheres and the concentric conducting spheres, and each of one is maintained at a constant potential. For spherical symmetric spaces, the solution of Laplace's equation is a plus b by r. These are the constants which are to be obtained from boundary condition. So first example that we are going to consider is the spherical capacitor. It comprises of two concentric spheres. The inner one is of a radius a and outer one has a radius b. We choose the coordinate system, so our origin of the coordinate system to be 1, which has its origin at the center, at the common center, and swap the Laplace's equation. For points here there is no charges, so the potential satisfies for Laplace equation, which for spherical symmetry has the solution this. We assume that the outer sphere, that is the sphere with radius a, b, is grounded, and the inner one is maintained at a constant potential phi 0. So the first boundary condition is that phi, and the solution is phi is a upon b by r at r is equal to b. This is 0 is equal to a plus capital B upon b, which gives us A is equal to minus B by B. So the potential now becomes, with this condition, the potential now becomes phi of R is equal to B times 1 by R minus 1 by B. Now the second condition, phi at R is equal to A is equal to phi 0, which gives us B times 1 by A minus 1 by B. This is equal to B times AB, B minus A, or B is equal to phi 0 AB by B minus A. So the potential now becomes, this potential becomes phi of R is equal to, for B we write this, so phi 0 times AB minus A, B minus A, 1 by R minus 1 by B. This is the potential at any point within this for a spherical capacitor. Now we use as the second example, we shall use a A spherical conductor. We consider a case of spherical conductor. A spherical conductor is a sphere of radius spherical conductor. We know that the conductor surface is an equipotential surface and the potential within the conductor is a constant, and as the field within the conductor is zero, electric field within the conductor is zero. We consider a spherical capacitor of spherical conductor of radius A. So the solution is general solution of it is A, phi of A is equal to B by R. For internal region, the internal region is R less than equal to A equal to 0. You see that this term B by R has a divergence at R is equal to 0. So we conclude that there should be no term of this sort, that is B is equal to 0. So phi internal is R is equal to A is equal to constant. Potential is constant. For external region, for which R is greater than equal to A, phi must go to 0 as R tends to infinity. As R tends to infinity, this term dies off, but this term persists. So we conclude that this A is 0 for external region, and for external region potential is B by R. Now we know that the potential is continuous across the boundary. So we have phi I and phi I at R is equal to A is equal to the phi potential at the surface, which is equal to A. So we get it as phi of surface value. Now if we put apply R is equal to A over here, that is phi I at A is equal to phi S is equal to phi E at R is equal to A. We have phi S is equal to B by A, or B is equal to A phi S. So that the potential at the external point becomes phi external becomes phi S A by R. So far an external point is concerned, the potential falls off as 1 by R. So as if the entire charge may be assumed to be concentrated at the center of the spherical conductor. This is what we have obtained from Gauss's theorem. So this much is the for the cases of spherical symmetry. Now we shall switch over to the case of azimuthal symmetry. These solution of Laplace's equation with azimuthal symmetry has immense application in electrostatic and magnetostatic. As per syllabus, we shall consider only few cases of electrostatic only. Before going to that, we shall use the boundary condition. The boundary condition is that the divergence of D is equal to rho. This leads to D2n minus D1n is equal to surface charge density sigma. Now for surface, when the interface is the spherical one, the dn, the normal component is defined as vector d times normal to the boundary. So if we have two regions separated by a spherical boundary, This is region 1 and region 2. Everything in region 1 are denoted by suffix 1 and every physical quantity in the region 2 is denoted by suffix 2. So we choose the coordinate origin to be the center of the sphere. So on the surface, the unit vector n cap is nothing but r cap. So for region 2 it is positive r cap and for region 1 it is negative r cap. And furthermore, D is given by epsilon E is equal to minus epsilon grad phi. It's the electrostatic potential. To avoid confusion with phi or theta phi, we use this one. So this condition becomes minus epsilon 2 grad phi 2 dot n2 Now we know that gradient operator in spherical polar coordinate is this. So when this is dotted with r cap, only this part survives. So this becomes at the surface, we assume it is r is equal to a. Here is a sign. There are two negative sign, and this is the boundary condition relating to the normal component of displacement vector in terms of the electrostatic potential. If there is no free charge density on the surface, then this is equal to this. This is the one boundary condition. The other boundary condition is that for electrostatic field curl E is equal to 0, which leads to the fact that E1t is equal to E2t always. Now if we consider this is the surface boundary interface separating two media, then the tangent vector E lies in theta phi plane. So to say that this part theta cap by A del phi 2 del theta at r is equal to A plus phi cap by A sin theta del phi 2 they are equal. That means this part is equal to this, because this relation is valid for all theta phi. Valid for all theta and phi. That is, this part is equal to this part and this part equal to this. That is del phi 2, del psi 2, phi 1 on the boundary is equal to del psi 1 del theta the boundary and del psi 2 del phi at the boundary is equal to at the boundary. The simplest solution is phi 1 is equal to phi 2, which satisfies this condition. So the other boundary condition is phi 1 psi 1 at r is equal to a, all theta phi is equal to psi 2 at r is equal to a. So these are the two boundary conditions that will be of use in future cases. So we come to the spherical symmetric cases. We shall apply this to spherically symmetric cases. As the first example of this chart, we consider a spherical conductor, azimuthally symmetric, recall that the solution is r theta phi, summation over L is equal to 0 to Al at to the power L, Bl at to the power minus L plus 1, and since the conductor, the system under consideration includes z-axis, so this is considered to be 0, and we assume the solution to be in the form L is equal to 0 to infinity, Al at to the power L, Bl at to the power minus L plus 1, Pl cos theta. This is the solution. So this is the sum. We consider a spherical capacitor, spherical conductor. In an existing uniform field. So the situation is that we have a conductor in the form of a sphere, and the sphere is placed in an existing uniform electric field. So the uniform electric field means E means E0 is a constant vector, so that its magnitude and direction both remains the same. We could choose the constant vector to lie in any direction, but the calculation drastically simplifies if we choose it to be like this, k cap E0, because z-axis is the axis of symmetry, is the axis of symmetry. If we choose the electric field to lie along the z-axis, then for sphere, when a sphere is placed in this existing electric field, the positive charges will be pulled pulled in this direction and the negative charges will move in opposition. But if we consider a strip like this, then these charges, the charge separation will be same on the at all points on the strip. That is to say, the system will have azimuthal symmetry if we choose the constant electric field to lie along the z-axis. If we choose the field to lie in any other direction, then the physical situation remains, although the physical situation remains the same, but the mathematical calculation becomes very much complicated, because firstly the system will no more have azimuthal symmetry. So we choose this to be the constant electric field, and if we write this in terms of potential, this should be del phi 0 del z, because E0 has only z dependence, and the potential representing E0 is written as this. If we integrate this, we get phi 0 of z is equal to minus E0 z plus some constant c. If we recall that z is equal to r cos theta, and this cos theta is P1, Legendre polynomial of order 1, so this is P1 of cos theta, so we can write it as c times P0 cos theta plus, because P0 cos theta is 1, and minus E0 r P1 of cos theta. This is the potential corresponding to the uniform field. So our geometry is like this. This is the uniform field E0, and the potential given E0, we write it as k cap phi 0 z, and there where phi 0 is given by, in terms of r theta, is given by c E0. I am not writing the argument cos theta minus E0 r P1. This is the potential due to the existing field. If we move far away from the field, from the sphere, the potential will be this there. Now we come to the solution. So, at every point, at internal and external point, the potential will be given by the solution of Laplace's equation, and basically of this. So for internal region, is this. Internal region extends from 0, r is equal to 0 to a, that is, it includes r is equal to 0 part. If we put r is equal to 0, there is the divergence, so there is no b term. We have only this term. So for internal region, r theta is L is equal to 0 to infinity a m r to the power L PL of cos theta, which is finite, which ensures the finiteness of the solution. Then for external region R extends for R is less than infinity greater than equal to A. So as R tends to infinity, there may be a divergence arising out of this form, and we have phi external as R tends to infinity, all value of theta must tend to phi 0 of r theta. Let us call it E0, and so this basically must tend to this form. Wherefrom we conclude that A0 should be C and A1 should be minus E0R. So if for external region at R theta we have C0 P1 minus E0R P1, sorry, this is P0, then this term summation over L from 0 to infinity BL R to the power minus L plus 1 PL of cos theta. Let me explain this part once more. The general solution of Laplace's equation with spherical symmetry, with azimuthal symmetry is this, and this solution assumes that z is equal to 0, z-axis is included within the system. So this solution must, we must not have Legendre function of second kind in the solution. So we have set this part is 0. Now for internal region, r is equal to 0 is there. If we put r is equal to 0, this term shows a divergence. So we consider that BL is 0 for internal region. So for internal region, the solution is this. This is because as phi I 0 theta is finite, and this value is A0. This is finite and this value is simply A0. And for external region, the solution, the R extends from A to infinity, and potential, as R tends to infinity, the potential must be the potential RD, which represents the existing uniform electric field. That is, the potential must go to psi 0 in the asymptotic region. So this says that only A0 and A1 will be there, and all other A's are 0. So A0 is C0 and A1 is minus E0R, and all other A's are 0 but all B's are there. So this is the solution. So this that as pi ER tends to infinity, all theta must tend to phi 0 at R theta. So these are the solutions. Now we know that the potential matches on the surface. So the first boundary condition is that the potential is continuous at R is equal to A, all values of theta. If we apply this one, we get this is A. So from the left hand side we have L is equal to 0 to infinity AL, A to the power L PL. This is also the surface value of the potential. This is the surface value of potential, which is a constant. So this may be considered to have be the coefficient of P0. And from the right hand side we have, from right hand side it is C0 P0 minus E0 AP1 plus summation over L BL A to the power L plus 1 PL. This relation is valid for all values of theta. That is, it is an identity in theta. Sorry, identity in PL of cos theta. That is, the coefficient of every order of Legendre polynomial must be same on the left as well as on the right. So the coefficient of P0, it is A0 is equal to phi s, and on the right hand side we have C0 minus plus B0 by A. So we get a relation between A0, C0, this is A0, C and B0. If we choose, the situation becomes very simple if we choose C is equal to 0, because C is the constant part in the potential, and we are interested about or so to say that experiment is not susceptible to potential. If we change the potential by a constant value, the force that a charged particle experiences remains the same. So we can keep the constant term in phi 0 there, or we may not keep it. If we keep the phi, if we put C0 to be 0, the calculation becomes very simple. Otherwise, we have to carry with this term. And if we equate the coefficient of P1, you see that in the left hand side, the potential on the left hand side becomes constant, and we have on the right hand side only E0 A times B1 by A square to be 0. Because the potential on the surface is phi s, so it has only the coefficient connected to P0. For P1, the coefficient is 0. So the potential for internal region, this becomes a constant, that is phi I r theta is simply A0 is equal to phi of surface value. It has only single term, and this gives us that B1 is equal to E0 upon A cube, and this becomes B0 is equal to phi SA with C is equal to 0. So what we get, this external region, this potential is no more there, so this part becomes this part simplifies to, if we set C0 as 0, so this is E0R cos theta, E0R cos theta from this part, then B0, where B0 is B0 by R plus B1 R square cos theta. And if we compare other powers of other higher coefficient of other higher orders of Legendre polynomial, they are 0. So all BL with L greater than 1 is 0 identically. On putting the values of E0, we get this is E0 R cos theta for B0 it is phi s a by r, and for this value it is E0 a cube r square cos theta. Now recall that this is the potential corresponding to existing electric field, and this is the potential for outer region or external region corresponding to the conductor. This part of the solution, this much up till now we have obtained the solution without going into the physical situation. In the conductor there are plenty of free charges and there are atomic ions. If this conductor be placed in an electric field, the positive charges will move in the direction of the electric field. If these positive charges are the atomic ions, they will be shifted by small amount as they are massive one, and the electrons will move a larger distance. However, there will be charge separation will occur, and so to say, if the conductor is placed in an electric field, it will behave as a dipole. It will behave as a dipole, and more or less dipole. If we look at the situation from multiple expansion point of view, the potential at an external point due to this induced conductor may be expanded in terms of monopole, dipole and other higher order terms. This calculation shows that so far as external point is concerned, there is a monopole contribution and this is the dipole contribution of the induced conductor. If the conductor were grounded 1, then the charge density on its surface or potential on its surface would be 0 and there will be no monopole term. Only term is the dipole term. And this is the potential due to monopole term. So this is the potential due to monopole term, which becomes 0 for grounded conductor, and this is the potential for induced dipole term. We could get the dipole moment from here. We know that the dipole potential is given by, recall that dipole potential is given by 1/4 pi epsilon naught P dot R by R cube, which becomes 1/4 pi epsilon 0 P cos theta by R square. By comparing this, we get P by 4 pi epsilon is equal to E0 a cube. So from this we can get the dipole moment of the conductor, and we can also get the polarization, which is the induced dipole moment per unit volume. So this is the dipole moment, and polarization will be P by 4/3 pi a cube. This is the polarization. If we want to write this in vector form, P is the polarization, P is around k cap P, and this dipole moment and capital P is also in the direction of k cap. That's all for today.